Hi guys, Miss O'Connell here. So today I'm going to try out using my phone as a document camera. So just like you, I am also in school. I'm technically getting my master's right now. And from staring at the computer all day, grading, recording videos, and then going to school, my eyes are killing me from staring at the computer. So I'm going to try and use document camera today to record. Based on the survey that we took in class yesterday, we had a pretty even split between three of the topics. So we're not going to be talking about magnetic fields, but we will be talking about circular motion, a little bit of special relativity, and then circuits. So circuits actually won the vote, so we'll be definitely talking about circuits. We're going to combine a little bit of circular motion and special relativity together due to how close those two topics were. Okay, so let's give the document camera a try. Okay, so technically we know, based on Newton's second law, that in order for an object to move or accelerate, there must be a net force applied. Okay, so in order for us to have a constant acceleration rate, we need a constant net force to be applied. When objects move in a circular path, such as a planet around the sun, such as a cork tied to a string that we whip around our head, or your car as it takes a turn off a parkway ramp. In order for an object to make a circular path of motion, there must be some constant force being applied. In order to have a circular path, we must have a constant force and constant acceleration that is center seeking. Okay, so circular motion is pretty remarkable if you think about it, right? Circular motion is rare. You need a constant force that points towards the center of the circle, which we call centripetal. It's the Greek word for that. Okay, and it must be pointing towards the center of the circle at every instant in that object's motion. Okay, so it's pretty rare, pretty remarkable. We're going to first start out by talking about a very specific type of circular motion, in which we call uniform circular motion, which which we sometimes abbreviate as UCM, okay, which stands for Uniform Circular Motion. Okay, so it's a special case of circular motion. Do we know what the word uniform means? So if you go to a school, right, that wears uniforms, you wear the same clothes every day, okay? Meaning that the outfit you choose is constant. For uniform circular motion, the defining characteristic is that the velocity or the speed, okay, around that circular path is constant. So uniform circular motion is a special case of circular motion. Where an object or particle moves around a circular path of motion at a constant speed. Okay, so we should know by this point the difference between speed and velocity, okay? So let's again look at an object that's moving in a circle. Let's say I have a stopper tied to a string and I'm whipping it around the top of my head. Okay, so here's the stopper, here's the string, okay, and I'm whirling it around the top of my head. Okay, so this is a bird's eye view. At every point in its path of motion, the speed, okay, or a velocity vector, it'll point in the direction of rotation. So let's say our stopper's here. The tangential velocity, aka the speed of the object moving around the circle, is going to be tangent to the circular path. It'll point in the direction of rotation, and it'll be a constant rate. Notice how these vectors are the same exact length. So regardless of where the stopper is in that circular path, it has the same speed, so the length of these vectors are constant, but technically, we notice here that although the length is constant, the direction changes at every instant. Okay, so we know that speed is the magnitude of the velocity vector. So what that means, right? This velocity, this constant speed, we call this the tangential velocity. That variable that we use is v, capital V, subscript t. Okay, so this is the constant speed in which an object moves around a circular path. Okay, so that value, the magnitude, again, magnitude from our first unit. Magnitude is the number or the value. Okay, that's always constant, doesn't change. The symbol that we use for that is two parallel lines on either side of our variable. So if we're saying the magnitude, that's the symbol for that. Two parallel lines, our variable, two parallel lines. Okay, so the magnitude is constant. But the direction changes at every instant. Right? Every second, the object will have a different location in its path of motion. At that time, the magnitude of the velocity, aka the speed, is constant, but the direction that that vector points will change. We call that constant speed the tangential velocity because that velocity vector is tangent to the circular path, meaning that it begins on the curve, begins on the path of motion, and is tangent to that path of motion. Okay, so if we're saying that tangential velocity is equivalent or similar to speed, right? If we think way back to our first unit ever, right, the speed of an object moving in a circle, or speed of an object in general, would be the distance divided by the time. Okay, using this as a model, we're going to come up with an equation for tangential velocity. Okay, so technically, instead of S for speed, we're going to use V sub t, which stands for tangential velocity. Okay, the distance that you would travel if you moved around a circular path, the distance, right? We know that distance is total ground covered. It accounts for every step that you take, divided by the total time. Okay, so distance, speed, distance is the total ground covered. So the total ground covered by this stopper, how could we find that? So hopefully you're thinking back to math class, right? The distance around the outside of a circle, we call that the circumference. So we take the circumference and we divide it by the time it takes to travel that circumference, or to make one complete rotation. The circumference of a circle is 2 pi r. Right, if you think back to math class, we know that circumference is 2 pi r. The time that it takes, so think about this, the time that it takes to make one revolution or one full circle, what do you think we call that? If you think back to our last unit, right? Period, for simple harmonic motion, is the time it takes for one cycle or oscillation. So what do you think time per revolution would give us? Exactly, the period. So the tangential velocity is equal to the circumference, which is 2 times pi times the radius of the circle, divided by the period, which is the time it takes to make one complete cycle or revolution. Okay, so V sub t is tangential velocity. Measured in meters per second. R is the radius of a circle, measured in meters. T is the period. In this case, it's the time it takes for one revolution or one cycle. Measured in seconds. And there's our first relationship for how we measure motion around a circular path.